Okay, here's a really quick video on integrals where the solutions involve the inverse trig functions. Okay, it's a very long title, but a quick video. So here we just need to remind ourselves, we've got the derivative of inverse sine is 1 on the square root of a squared minus x squared. We got inverse sine of x on a. And then same with these. Remember the tan one's a little bit different. Inverse tan of x on a equals a divided by a squared plus x squared. Okay, so now that we remember that, let's dig into a few integrals. What would we get if we were trying to take the integral of -3 on root 16 minus x squared dx? Okay, well, we could try and get it into one of these forms to help us out. So we could go take out the 3, and we could have 1 on square root, -1 on 16 minus x squared dx. And we're thinking, oh yeah, that now looks like this inverse cos, so now we've got 3 times the inverse cos of x on a, and a is 4 plus c. Now, we had a few options here. We didn't have to do it that way. We could have, if I rub that out, we could have put it into the form where we've got an inverse sine here. So we could have gone -3 outside the bracket, right? And then get positive 1 on 16 minus x squared dx. And that would have left us with, now we're in this form, -3 inverse sine of x on 4 plus d this time. So this d might be different if we're using sine in comparison to our c for the cos, but still a valid answer to this question. Okay, so that's a fairly easy one. Let's try one more. 3 over, we're going to take an integral of 9 plus x squared dx. Now this is looking more like this. In fact, a and a squared dx, that's looking very similar, where a is 3. So I can just put it straight in. Inverse tan of x on 3 plus c, and we're done. Okay, what if this was a different number? What if this was 5? What would we do then? How would this change it? Okay, well, I want it to be a 3. So let's take out the 5, replace it with a 3, and because I've times this by 3 here, I've got to divide by 3 here, and now the whole thing becomes 5/3 of that. So regardless of what this number is, I can usually change it to make it a valid a here. Okay, all right, let's try it on. Let's try something a little bit trickier, something a little bit different. You might not be able to see it straight away. X squared plus 2x plus 2 dx. Okay, and you're thinking, well, this doesn't really look like one of these. It might look like this one the most, but it's got this other x in here. Well, let's rewrite it. Let's factor the bottom. Now, when we factor the bottom, we're going to have to complete the square here because this doesn't have any other rational factors, so it's our only option. So let's go with 3 on integral of x plus 1 squared plus 1. Okay, so that's completing the square on that, gives me this dx. And all right, it's not quite in this form, so let's take out 3. 1 on x plus 1 squared plus 1 dx. Now I could make a u substitution here because I know that if u equals x plus 1, let's just do it. We'll do it really quick. Let u equal x plus 1 and du dx is equal to 1, so I can make the substitution really easily, which is lovely. Great, 1 on u squared plus 1 du, right? Du now, not dx, because I substituted in this du dx here, because it's equal to 1, so I'm not going to change it any. And now I've got 3, the inverse tan of u on 1, which is just u. And I know u, resubstitute it back in, is x plus 1 plus c. There we go. And we've got it, that's it.